Yes. So let's assume that we have a random variable so that x omega belongs to the set 0 and 1 for all omega. Okay. So x is now a function from omega to the real line. Is x measurable? Yes or no? Well, we need to study some pre-images again. Yep. So, for example, we could look at what's the pre-image of the point, the set which only contains one point, the point 1. Let's call this set E. And is this measurable? So is this in the sigma algebra? Yes or no? It depends on the set E. So both can happen in principle. So we actually, you can check that x is measurable, or let's say so. Let's say actually this way. Okay, I'll clean this up for a while, and we conclude actually that x is a random variable if and only if E belongs to F. And this is the event that x takes the value 1. That's something that we could verify. If this is true, then also the other pre-images are measurable, actually. That's easy to kind of look because there are only 2 values, so basic logic, actually. Let's call it easy exercise. That's actually, to make this thing clear, this is going to be part of your homework. So looking at binary cases in this way. So what about the distribution of x? Again, we could look, okay, what is the law of x now? And again, we should look, okay, what's the pre-image of a set B? And again, we recall that it's the question, is x in B or not? And if you look at the pre-image of B now, so recall that omega is here, and then we have now the real line there, and we have 2 values, 0 and 1, where the random variable can take values. So we actually have 4 cases. If this pre-image is empty, if 0 and 1 are not in B, it's the full space if 0 and 1 are both in B. It is this set E if 0 is not in B and 1 is in B. It's the E complement in the remaining case. So 0 is a member of B and 1 is not in B. We have 4 different cases for the pre-image of set B. So think about, for example, B being this set here. So what would be the pre-image by X now? It's the set of points which map into 0. Yeah? And because E was the set of points which map into 1, so the rest of the points must map into 0, because we assume that X only maps into the set 0 and 1. So that's why this is now the E complement. And the rest actually of the space is E, so it's split into E complement and E. And now what we can conclude about the law, we can conclude that there are 4 cases. So there are cases 0, 1 minus P, P, and 1. And according to these 4 cases that we looked at, so this is the case where nothing is in B of the values. 0 in B, 1 is not in B, 0 not in B, 1 in B, and both values if they are in B, so then we get 1 here. So there are 4 different cases, and actually a short way to write this it would be to say that it's 1 minus P when 0 is in P. So we put the Dirac measure 0 of B plus P times the Dirac measure of 1 at B. So this is a way to conclude it, and we can conclusion is that actually here is that the distribution or the law of a binary random variable is equal to 1 minus Dirac measure at 0 plus P times the Dirac measure at 1. So kind of we use the plus and multiplication of measures in the natural way of as we would do pointwise plus of functions. So these are also functions, set-valued set functions. And this measure is actually also having a name. Remember, this is called the Dirac measure at 1. This is called the Dirac measure at 0. What is this measure called? It's kind of a convex combination of 2 Dirac measures. Also, what is P? Well, P is now the probability of the set E, which is the probability of X being equal to 1. So that's kind of the nickname of probability X taking value 1. So that's the set E as we defined here, the pre-image of 1. Okay. So what's the name of this distribution? It's named after maybe the first kind of important mathematician in the field of probability. Who was this person? Okay, it's hard to say who should be the first important person, but one of the most important persons to contribute in the field of probability in the 1713. So in the year 1713, there was a publication called Ars Conjectandi by Jacob Bernoulli. So this is why this distribution is called Bernoulli distribution with parameter P. So that's called the Bernoulli distribution. But this is the way how Bernoulli and Dirac are related. So of course Dirac lived 200 years later than Bernoulli, but the relationship is there. You get Bernoulli when you take a convex combination of 2 Diracs.